I'm here today to talk a little bit about Roblox's strategy of analytics for everyone. So some of you may not be familiar with what Roblox even is. Perhaps your kids have played it before or told you about it. Generally, Roblox is a gaming platform where you come to it on an app or the website, and millions of games are on this platform made by our creator community. Generally, we find that across our 79 million daily active users, the thing that really resonates the most with them and gets them coming back to Roblox and excited is when they get to play together. So today, we're going to be talking about a specific product called Creator Analytics that we build at Roblox. Generally, at Roblox, we try and build tools that empower our creators to make massive online experiences, and this is one of those tools. So we view Creator Analytics as a one-stop shop to find the most important insights and actions for a developer's game. Generally, you want to know things like how many people are playing your game, how it's monetizing, who's coming to your game. And this is relatively big business. Last year, we paid out more than $740 million to our creators. And so they really need a guide of how to know how to grow their game and what's important. And of course, being here, we're going to be talking a good bit about the back end, the underlying data infrastructure for how we run Creator Analytics. So we serve data from more than 10 million different experiences. We kind of use the term experience, game, and universe all interchangeably at Roblox. And we serve more than 9 million queries per day on a pretty small, just 100 core, 4 historical cluster. We want to keep the cluster small because we really want to serve these analytics for free to all game developers so that they can get insights, whether they're a new upstart or a big titan on our platform. Generally, our data infrastructure at Roblox is a pretty classic setup. We store most of our data on an S3 data lake. We do dynamic querying via Trino and Superset to do analysis and dashboarding. We use Spark clusters to do most of our ETL and big data jobs, and we use Airflow to schedule those jobs. Plugging into this with Druid wasn't too hard. We forked off the Airflow Druid plugin and added just a little bit to it so that we can submit Druid ingestion specs from Airflow. They fall into our normal Airflow pipelines. Druid reads off the data lake and makes the data available. For the Creator Analytics users, they come to their dashboard to see their different metrics. Their dashboard is converted into a data frame style query, usually dimensions and metrics that they want to know about, things like breakdowns, custom dates. Those are all converted via Cube.js from these dimensions and metrics into a Druid SQL query that's then returned back. So what actually is Creator Analytics serving? What's the value? There are dozens of different analytics pages that creators can learn anything and everything about their experiences. These are served by 22 data sources on Druid, comprising roughly 51 terabytes of pre-aggregated data. And we primarily serve engagement. That means daily active users, monthly active users, retention, funnel analysis, monetization. That's things like revenue, average revenue per user, sales, in-game economy metrics, and acquisition. Where are these users coming from? How are they coming to your platform? Should you be spending more on channels to get them there? And we also allow for complex filters, a lot of different breakdowns, dynamic date selection for all of these different categories. And we see more than 400,000 daily active users across all the different pages of analytics dashboards. So when we were designing this use case, we really wanted to focus on some of our most expensive queries, make sure that those were going to perform to our expectations, and that we were going to be able to solve the problem in a reasonably cost-efficient way. Primarily, we identified that we needed a web scale latency kind of solution for these most expensive queries. We view that as anything under 2 seconds. And our most expensive query we were imagining was distinct counts that parse more than 100 million users, usually as a monthly active user kind of query. And to make matters worse, we also want very complex breakdowns on these 100 million users that might exist in a single universe. And in our top universes, we see that there are 50,000 different dimensional combination groupings across dimensions like country, locale, new users, operating system, and more. And we wanted to do this all on a small, less than 100 core cluster so we could keep it cost efficient. So one of the key solutions that we identified early on that we really wanted to focus on was a big focus on approximation. We felt pretty confident that we didn't need to return exact numbers in all cases. Instead, we could return reasonably confident sketches to prove out our use case. Some of you may or may not be familiar with some approximate data sketches. We're big users of Apache data sketches, which Druid also integrated long ago and helps power especially queries like count distinct. There are several key features of approximate data sketches that we care a lot about. First, in our importance, is sublinear in space. So that means that as your data volume is growing, you are not eating more and more cost. In particular, this means that our top universes that have tons and tons of data are not growing to their full size, and the cost of the query becomes still manageable. Secondly is mergeability. Mergeability is particularly important in count distinct queries because the typical way to do count distinct is either load all of your IDs into a single map, which in our case wouldn't possibly work on a single node without some real weird conditions, or doing a global sort of all of your keys. And global sorts almost always require shuffles, and shuffles are notoriously expensive, network intensive, obviously not going to happen in less than 2 seconds. And finally, we care a lot about the mathematically proven error bounds. We need to know how do we tweak it to make it more accurate. What is the error range going to look like? What will happen in our worst case? How can we communicate this back to users? So we felt pretty good about the theoretical elements of Apache data sketches. They've done a lot of math to prove it out. I definitely recommend if you ever want to read their papers or their source code. It's some cool stuff. But moving on from the theoretical, we needed to load test this out, make sure that it was going to work for our particular use case in an efficient way. To do this, we loaded 6 months of engagement data into our test 100-core 500 GB Druid cluster. And primarily, we were testing HLL versus theta sketches. These are the two main approaches for doing approximate count distinct. HLL is pretty much universally considered the most space-efficient approach. And space efficiency here almost always translates to CPU efficiency because your queries are smaller. Generally, you can kind of see an example of how HLL works on the left. You take some ID, you hash it, you take some elements of the first, say 10 bits. Those become buckets, where then the rest of your identifier you take a max on. Your max funnels into the particular bucket from its identifier, and then you compute the harmonic mean over all your buckets or registers in this case. This is a provably somewhat accurate way to do count distinct, and you can show different error bounds for that. Generally, for most of our queries, we use HLL. It's more performant. It had what we needed. Theta does allow for intersection, which I'll come back to later, and offers some other functionalities. We found that we could merge 8 million HLL sketches. These are kind of like individual aggregates, and comprised roughly 25 megabytes in just 2 seconds. As a result, we felt like this system, that was really the load test we wanted to prove. We were able to do it in 2 seconds. We knew that this large MAU query was going to be possible, and we could keep going from there. Generally, when we're doing these tests on Druid, we really needed to test cold start queries. We have too much data to fit it all into cache without way exploding our number of historicals. And Druid is very eager to do mmap, which is great for performance, but hard for testing the raw loading time of off-of-disk queries. So we'd usually do key changes or slight changes to try and avoid that and make sure we were still testing accurately the cold start performance. We also were extremely reliant on decent local disk. I mean, not the fastest local disk, we're still using EBS, but way better than network storage. We tried out solutions like ClickHouse and DuckDB reaching out to S3, even with different kinds of pushdowns. There was just no way that that was going to approach the speeds we needed. And we also built out some open source user-defined aggregate functions from Spark or on top of Spark and Trino so that we can have full data lake binary compatibility of these approximate sketches. When we render it in our game engine, we can ship an event that carries a median or like an approx count or an approx median type of sketch all the way through to our data lake and then query it via Trino or Spark. Now, we felt pretty confident, but we did still run into some scale problems, in particular with Apache Druid, as we moved this into actual production. In particular, our MAU query, we'd kind of sized it first as just doing a large single-shot query, but our realistic query pattern was per day MAU. We needed to know, say, for the last 90 days, what was the monthly active users on each individual day. Doing this style of query really resulted in the brokers having to do a lot of work. Our naive query was, in essence, grouping by day, so the historical was just getting a per-day aggregate, shipping it back to the broker, and the broker ended up having to roll up more than 1,800 max-size HLL sketches. This was really a lot of broker CPU. We felt like we'd have to scale up brokers quite substantially to make it work, and was much riskier as a large spike on the broker could cause issues. So we ended up moving to an inline join MAU query. So we pre-built a date table for which dates were going to be needed. We copied it to each node. So in essence, we took some of the broker work, we shipped it out to each historical node. The historical did as much of the collapsing as it could based on what data was available on that particular historical, shipped it back to the broker, and the broker, in our case, had to do substantially less work. Now, this does mean that our query itself scales somewhat with the number of historicals. So if our data was spread across many, many historicals, then we wouldn't see the same performance gains. And this is okay for us because we're trying to have a lean cluster that's very performant. We want our historicals to be doing a lot of the work and be able to operate pretty independently. You can see in our breakdown of performance, this brought our query 5 times faster, roughly, reduced our broker CPU time by almost 50x. And you can see that the historical was doing a lot more work, which is what we wanted. We wanted historicals to do most of the query work as opposed to brokers having to do a big roll-up at the end. So we felt pretty good about our worst case query performance, but then we wanted to focus a little bit on how to improve average case, make sure that our overall cluster was going to perform very efficiently. One of the classic cases for performing average case, and the secret to Google Analytics and so many analytics use cases, is roll-up tables. This is generally where instead of importing raw data, where you have some key per unique identifier, you roll up to some number of dimensions and you aggregate your metric, or you pre-aggregate your metric columns. Pretty obvious for things like sums or counts. You can just add them together or do counts. For approximate distincts, it's still possible because of that mergeability property, and it works decently well. Generally, in a roll-up table, you have many rows that collapse to one, and there are a bunch of qualities of like how you sort it, how you do it. The worst case for these roll-up tables is as you increase your cardinality, as you take your cardinality very, very high, you pretty much lose all the benefits. Like if your cardinality equals your number of raw rows, then you're not gaining anything. You can imagine each added dimension as, in essence, another layer. So we calculate metrics on things like country and language for every single universe. So that means that we have like 200 countries and 50 languages, which thus quickly becomes 10,000 different breakdowns in a roll-up table. So just as you increase that cardinality, you lose some of the benefits. On the flip side, raw tables have gotten a lot better over time. Druid helped pioneer a lot of these techniques, but predicate and projection pushdowns really mean that we don't have to read as much raw table data. You can go specifically to rows you want, particularly if you have very detailed queries, like if I want to know how many users in Canada spoke Spanish and were over 18, there might not really be that many rows for that particular query. So going to the raw might not really be so bad. So we kind of came up with an approach that could extend roll-up tables through approximation and could potentially offer deeper gains, even with higher cardinality. So generally, your worst case in a roll-up table is when you have a query that needs a lot of dimensional breakdown, like you need to know several levels deep of dimensions, but you also, the number of raw rows that would still result is probably still in the millions or very high. So your raw table query is still also relatively infeasible. So we kind of envision this as if you took two data sets, kind of like country and locale, or country and language. We have a single universe, so we have one table that's a universe country table, and one table that's a universe language table. And much like you do with a normal join, we kind of envisioned an approximate join, where you merge, like if you're looking for Canada and Spanish for a particular universe, you can merge these two tables and find the intersection value, and then use that to get your actual estimate of how many users matched those qualities. And this works pretty well when the two tables have high overlap. In particular, the error scales inversely with the size of the intersection. So as your tables have high overlap, you'll do pretty well, and it'll scale relatively closely to the original sketch error, which is roughly proportional to the size of the union. And the nice thing about this is instead of having a product of dimension cardinality, where you had number of countries times number of languages, you just have a sum. So it's number of countries plus the number of languages. And this generally works because of how theta sketches work. The way that theta sketches work is generally you have kind of a top K list of the values that you're keeping. You do some uniform hash on whatever input IDs you want, but because you're keeping a minimum list of your values, two sets that have high overlap are also likely to have high overlap of your approximate set or your approximate theta sketch. And because of that, you can do relatively decently on the error rate. Of course, this also means if your two sets don't have high overlap, then your error can really explode. I mean, you can imagine a case where the denominator is 0 and your error is infinite. But that's actually also a good signal, because that means that probably the intersection of these tables doesn't have much data. So you could go out to a raw table and go and get each individual row. And that was kind of what we envisioned with this idea of a theta cube, that you could use the predicted error rate to determine whether you should go to a raw table, and in cases where you want to go more than 1 or 2 dimensions deep, you can do that approximate join connection. So in the end, we did a lot of math and planning around theta cube, but we found that really until the next level of scale that we have, it's not necessary. So a whole bunch of fun, but really what worked for us most efficiently was a very simple low cardinality roll-up table where we removed country and language entirely. 99% of our queries don't ever use country or language, and thus most of our performance, most of our queries are under 3 milliseconds in average query time. It's very performant. We don't eat too much CPU with the vast majority of our queries. We're doing less roll-up. And when we do need those, we actually have more total CPU available because we're mostly operating on queries that don't even touch those dimensions. So this was one of our average query optimizations. We also put a little bit of focus into the cost of query should be inherent in our design. Generally, we want low-cost, high-value queries to be on home pages, landing pages, everywhere. You know, those are cheap. We can just, Druid can serve tons and tons of those queries. We serve like hundreds per second. And then we want high-cost, high-value queries to be a little harder to reach. Maybe you have to drill down a little bit. Maybe 90-day MAU isn't the first thing you see on your page, but you can go find it. If you need to know, you can find it. And because we're prioritizing low cost, we have CPU available to serve it. And then we try and really disallow high-cost, low-value queries. When people want to merge in that kind of stuff, we'd ask questions, and we don't offer a full SQL interface for people to just query anything. They have to go through our translation system. So generally, our cluster details, in order to really protect the cluster, we have a lot of aggressive timeouts. We have a 12-second historical and 8-second broker timeout. This prevents extremely expensive queries from dominating. In particular, we have a slightly higher historical so that on retries, some of it might be cached. And we also lean a lot on prioritization. Big queries, we try and downgrade. We reduce their priority. And queries on high cardinality, like country and locale, we also penalize. Generally, this is our cluster setup. We run 2 query, 3 coordinator, and 4 historicals. And for this reason I mentioned before, we want to prioritize a small number of large historicals so that the approximate merge on the broker is simple. We could also separate out that particular data source into its own data tier so that we can keep it on a small number of historicals. We do all of our deployments via Helm chart on EKS. It's the imply Helm chart. When we need to do advanced storage swap operations like increasing storage or making changes to the storage, we generally do kind of a blue-green data tier deployment where we spin up a whole new set of data nodes and then wait for data to replicate and roll them down once it's finished. And we do a lot of cluster performance analysis via Clarity. In particular, on Clarity, we override the SQL query ID with a particular ID for the universe, so we can quickly group by and spot hot universes that are kind of doing weird things. We do most of our ingestion actually via batch in this system, and we minimize complex rollups. We want generally people on our data lake to use our Spark CPU to do big rollups, big ETL jobs. They should just be copying data into Druid for serving in our case. And we use this special function, complex decode base 64, to load sketches exactly as they are into Druid. As far as final outcomes go, we achieved 10 times average query performance. This was largely via the rollups and usage of approximations. 100 times worst case query performance. This was largely from redesigning the query and making it heavier on historical, along with the prior average performance. And we expect a large reduction in potential cost on our data lake via using DataSketch user-defined aggregate functions that we've added. And Roblox employees can create and surface these new data sets through different PR workflows and our Airflow Druid operator. We also, just yesterday, actually released tooling, our user-defined aggregate functions that we use for Spark and Trino can be found on github.com/roblox/data-tools. And those are available for use. We just wanted to publish how we use them, along with some Druid workflows showing kind of how we work with these approximate data structures. Finally, in the future, we want to do some more dynamic funnel intersections. This will probably call back to some of our ThetaCube work, where we can dynamically choose different dimensions to do approximates on. We want to increase real-time usage, and we also want to make internal querying a little easier at Roblox on our data sets. And that's it.